Moments. Here we have two people of equal weight balanced on a seesaw as they are equal distances from the pivot. These two people are also balanced or in equilibrium, but now the smaller person has moved further from the pivot, the larger person closer to the pivot. They can do this because of moments or turning effects, and these are given by the force, in this case the weight of the person, multiplied by their perpendicular distance from the pivot. When in equilibrium, the sum of the clockwise moments, the clockwise moment here given by the smaller person, is equal to the sum of the anti-clockwise moment given by the larger person. This is known as the principle of moments. When answering a question, don't forget to state the when in equilibrium part. In terms of symbols, if we say this person has weight 1 and is distance d1 from the pivot, this person then has weight 2 and is distance d2 from the pivot. From the principle of moments, we can state that w1 d1, which is the moment given by the larger person, is equal to w2 d2, the moment given by the smaller person. Now to explain what's meant by the term perpendicular distance from the pivot. Here we have a lever at an angle, pivoted here, and the force is exerted downwards here. The perpendicular distance is this distance here, the distance at 90 degrees from the pivot point to where the force acts. Here we have a slightly more complicated case to explain the term the sum of the moments. In this case, one larger person on the left, providing an anti-clockwise moment, is balanced by two people on the right, providing a clockwise moment. I've used the same notation as before, with this person having weight 1 and being distance 1. These two people now are distance 2 for weight 2 and distance 3 for weight 3. So the sum of the anti-clockwise moments, which is just w1 d1, the larger person's moment, is equal to the sum of the clockwise moments, in this case w2 d2 plus w3 d3. Let's look at an example. A 300 Newton child sits 1.6 meters from the pivot on a seesaw and balances another child 1.8 meters from the pivot. What is the weight of the second child? Well, we've got our equation weight 1 multiplied by distance 1 equals weight 2 multiplied by distance 2, and so we can rearrange for weight 2, the weight of the second child. Putting in the numbers, weight 1 was 300 newtons, distance 1 1.6 meters, and distance 2 1.8 meters, giving the weight of the second child as 267 newtons. A quick check, they are further from the pivot and so must weigh less, and in this case they do weigh less than the 300 newtons of the first child. The 300 Newton child now moves out to sit 2 meters from the pivot. The lighter child stays still and is joined by a friend of weight 180 newtons. Where must the friend sit if the seesaw is to remain balanced? Well, now the moment of the 300 Newton child on one side of the seesaw must equal the sum of the moments of the second and third child. We want to find d3, the distance of the third child from the pivot, so we can rearrange this formula to give d3 being equal to the moment of the first child minus the moment of the second child divided by the weight of the third child. Putting in the numbers, the moment of the first child is 300 newtons multiplied by 2 meters from the pivot. The second child we found had a weight of 267 newtons, and they are a distance of 1.8 meters from the pivot. And the third child has a weight of 180 newtons. This gives the third child's distance from the pivot as 0.66 meters. A common problem is to be asked to find the weight of a meter rule using moments. First, we must find the point at which the rule will balance. This is called the centre of mass, and we can assume for the calculation that all of the weight of the rule acts at this point. If the rule is uniform, this will be at the centre. Then we use a known weight to balance the ruler off-centre. You'll see we've moved the pivot point to the left. These weights here are providing the anti-clockwise moment. The weight of the ruler will be acting around about here, providing the clockwise moment. So I'll mark this as W sub W, the weight of the weights, and this has a distance D sub W, and the weight of the ruler here, W sub R, is acting this distance from the pivot. Using the principle of moments, I know that the moment given by the weight is equal to the moment given by the ruler. I can rearrange for the weight of the ruler and put in the numbers I've found. Clearly it would be better to do this several times for several distances and weights and find the average value. Now back to our earlier seesaw problem, but I'm going to add in a force W sub S here, which is the weight of the seesaw. And I can also now add the reaction force, which will be acting up from the pivot, and as the seesaw is not accelerating up or down, we know that the reaction force R, the upwards force, must be equal to the sum of the downwards forces, W1, the weight of the larger person, W2, the weight of the smaller person, and Ws, the weight of the seesaw. I'm now going to see what happens if I take moments about W1, about this point. What happens now is this person has 0 moment, as they are 0 distance from the pivot. So I can write RD1, the anti-clockwise moment provided by the reaction force and its distance from the pivot, is equal to WSD1, the clockwise moment provided by the weight of the seesaw, multiplied by its distance from the pivot, plus W2, D1 plus D2, which is the weight of the smaller person, multiplied by their distance from the pivot point. But here I found that R was equal to the sum of the 3 weights, and so I can expand this out as W1 plus W2 plus Ws D1 is equal to the clockwise moment provided by the weight of the seesaw plus the clockwise moment provided by the smaller person. Expanding out the brackets on both sides gives W1 D1 plus W2 D1 plus Ws D1 is equal to Ws D1 plus W2 D1 plus W2 D2. So we have a Ws D1 on the right and the left. We can cancel those. We have a W2 D1 on the right and the left, so we can cancel those, and we end up with W1 D1 is equal to W2 D2. This is the same expression as we found previously, and this shows that we can take moments about any point we wish. We'll see how this is helpful in the next slide. Taking moments about any point we wish is important in tackling 2 support problems like this one. Here we have a uniform beam. This is the beam here. Uniform just means that we can take the centre of mass as acting at the centre of the beam. It's resting on 2 pillars, A and B, and we're asked to find the forces exerted by the pillars, which I've called RA, reaction force A, and reaction force B. I've marked in distances here, distance A to the weight and distance B to the weight. What we can do now is take moments about A, about this point. This means that RA has 0 moment, as it is 0 distance from the pivot. So now, weight multiplied by distance A is the clockwise moment provided by the weight of the beam, is equal to RB, reaction force B, multiplied by its distance from the pivot, dA plus dB. That's this force here, RB, multiplied by this distance. we can now write that RB, reaction force B, is equal to this expression. To find reaction force RA, we could carry out the same procedure, but taking moments about this point, or knowing that the downward force W must be balanced by the two upward forces RA and RB, we can write that RA is equal to W minus RB. Finally, to look at an example using numbers. A uniform beam, the uniform, remember, means we can take the centre of mass as acting at the centre of the beam, 10 metres long of weight 1000 newtons, is supported 1 metre from either end by cables. A person of weight 700 newtons is standing 3 metres from one end. Calculate the tension in the cables. Well, firstly we need a clear diagram. So here I have my 10 metre beam, and the cable acting here will have tension T1, 1 metre from the end. The cable acting here has tension T2 and is 1 metre from this end. The person here has weight 700 newtons, and the weight of the beam acts here at the centre of 1000 newtons. This distance here will be 2 metres, the person is 3 metres from the end, and this distance was 1 metre, and this distance here will be 2 metres. This distance here is 4 metres. Now the forces I'm trying to find are T1 and T2, so if I take moments about either this point or this point, it means that these unknown forces will have zero moment, and so will be eliminated from my equation. I'm going to take moments about T1. So now I have T2, which is the anticlockwise moment provided by this, multiplied by 8 metres, which is this distance, must be equal to the clockwise moments of 700 newtons times 2 metres, the clockwise moment of the person, plus 1000 newtons times 4 metres, the clockwise moment of the beam. I can now rearrange for T2, and I find that T2 is equal to 675 newtons. I could now take moments about here to find T1, or, more simply, I can just say that the sum of the downwards forces, the 700 plus 1000 newtons, must equal the sum of the upwards forces, T1 plus T2, and so T1 is equal to the downwards forces 700 plus 1000 newtons minus the upwards force we already have of 675 newtons, meaning T1 is 1025 newtons. That seems about right. The person is closer to T1 than T2, and so T1 is providing more of the upwards force than T2.